So hello everyone, my name is Bruno, I work for Meta, and this is just supposed to give you a quick look into how compile time looks like for if you decide to use ClangIR in your compilation pipeline. So, a brief background here. What is ClangIR? ClangIR is a new IR for Clang that sits between ClangAST and LLVM IR. So if you're looking at the traditional way Clang usually builds your final object codes, you're going to go from AST to ClangIR, ClangIR to LLVM, and then traditional passes. It's a way, ClangIR is basically a way to represent more of the semantics of C and C++, so that you can write more specific analysis and think about maybe some aggressive optimizations and things like that. And another way to use ClangIR would be to move your compiler to the MLIR substrate. That basically means that you can use all the goodness that we've been hearing about for some years now of what MLIR can provide from your C and C++ source, right? ClangIR right now is part of the LLVM incubator. And thanks to our colleagues at NVIDIA, it's been upstreamed. We're about 30% in lines of code, kind of now part of upstream. And it's moving fast. We have 3 or 4 people working on it. So I'm very happy that this is happening. So, before I show some numbers on the actual compile time, if we're talking about giving a status with the open source tests we currently have, basically looking at the LLVM test suite, right now we can build 91% of single source benchmarks, which is kind of cool for showing correctness and the things we can already do on top of existing very common programs. If we look at multi-source, that coverage is around 80% these days. And on CTMark, which is actually one of the good benchmarks for compile time, we can only build 3 out of 10. And I'm going to start showing how well we do with those, right? So, first of all, the parallel line composed of 27 C source files. If we're looking at O2 pipeline, right now the regression, quote unquote, is around 20% on an asserts build, release asserts, and around 10% on just a release. If we look at the O0 pipeline, that's a very different number, right? The reason is because most time in the compilation pipeline is spent with optimization. So you would expect that whatever we're introducing extra here is kind of hidden a bit by the burden of going through the optimizations. Looking at another example, we kind of have slightly bigger numbers on the O2 pipeline, slightly bigger than 20%, and slightly lower on the O0 pipeline. Not 100%, but close. This is another data point. It's a bigger one, 50 source files. So this is, the accumulated time of all those sources, right? Because individually, they're not so big, so it's easier to show the actual footprint we get. And the one that is going a bit more off the charts is the LLVM code. Here we get 55 to 60% slowdown on the O2 pipeline, and a slightly higher on the O0 pipeline, around almost 200 at times. So let's look at just one case study, right? We showed how we can do if we're collecting the overall numbers for multiple source files. And now if we're just looking at one, right? The hard part here is that some of those programs, they don't take a lot of time to build. So I pick one that takes half a second, which is one of the best I could get around multi-source. And if we look at O0, there's a 50% increase. So let's try to see where things are happening here. So first of all, the traditional Clang pipeline, if you look at the AST to LLVM conversion, that's very fast. It's only 15 milliseconds. And I wouldn't expect anything worse than this because there's been 20 years of development. And that thing is highly it has a high quality bar. So if we look at what we're doing right now, it's quite bigger. It's 300 milliseconds. So let's try to dig a bit and see why. So the biggest number is already where most of time is spent with CIRGen, which is actually where we do AST to ClangIR conversion. This is like completely unexpected because, if I would naively think about this, I would first think that all the other, lowerings and other things we do on top of MLIR proper would be slower. So also, like, codegen is where we actually want to be fast. You don't want to be doing like a lot of crazy optimizations. You want that to be just, convert from AST to ClangIR and let later passes do the job of analysis or optimization. So this was quite surprising, and I'm like, well, let's see what's happening there that we should like mitigate. Note that this is a C++ source. So looking at that specific file, we saw, it's basically partitioned between emit deferred, because in C++, a lot of the times, if you're emitting lots of constructions and destructors, those things are emitted after you actually go through a full pass on your translation unit. So that's, not too bad, 24 milliseconds. But there's also a function called apply replacements that, because, ClangIR, differently from the LLVM, doesn't have opaque pointers, we actually have to do a lot of symbol uses replacement, because that's the strategy required for some of the aliases, constructors and destructors. So basically, almost all the time is spent there. That was, a very interesting surprise. I'm like, we never look at this. We never did any work trying to mitigate compile time so far. We just start measuring. So looks like one of the biggest problems we have, it's not a super hard problem to fix. We can go to a different strategy on how we do bookkeeping on those entities and just do a better job and maybe reduce this like to a more sane amount of time, like 20 milliseconds or so. So yeah, the first thing we look at is actually looks like a low-hanging fruit. And now, like, if we take a holistic view of all multi-source files, we have about like 57 of them, at least that we can build in this mode for O2. And I actually filtered only the things that take more than half a second to build, because otherwise it's just too much noise. And basically, if we look at up to 20% slowdown, we cover like 20% of those tests. Between 20 to 30% slowdown, that's actually where most of the programs are. We have around 30 sources. And only 7 that actually break this limit of like 30% slowdown. And as you can see, most of them are under 50%, but there are a few on top, and there's a crazy one about 300%. So there's probably doing something stupid there as well that we need to look at. So the conclusion here is that I see this as a lot of opportunity for improvements. I was thinking the numbers would be way worse, to be honest. I'm actually quite happy about them. And as we work together with open source and other companies, like eventually, probably not too far from now, we're going to be drilling and trying to like make this more sane, keep this on the web page, so that our users, know how much they're going to be paying for using those features. And as we add more C++ support to ClangIR, we can measure this in other code bases that, I would love to build x86 AsiaLLVM.cpp and see how long that takes with ClangIR, but we're not just there yet. And as we actually go about writing analysis and transformations on top of C and C++ things, I would expect our pipeline to take longer on the optimization side as well. And there's a recent talk a year ago about like some good practices to avoid doing slow things in MLIR, and we probably should take a look at those and see if we're not like infringing any of those things. One quick note is that I was expecting verifiers to be more expensive. And well, turns out we only run it once in the pipeline. So maybe we multiply this as if we run after all the passes. But it was quite a good number. And there's probably something else we want to do with like ClangIR's LLVM, which is taking more than the other things. There's probably something silly we were doing there that we need to look at. But yeah, we don't have time for questions, but hit me up on the hall if you want to discuss anything. Thank you.